So you find this treasure map, and you decide you need to look for this treasure. You're examining this treasure map on your desk one night. It starts getting a little bit dark. So you turn a light on. The light, the lamp that you're using, has a wire that goes from the plug-in over there, goes down through here, underneath this map, and over here, okay, where you have the lamp. You got a compass right here. And the compass needle is pointing this way. It's pointing toward, well, what we usually call north, but we know is really magnetic south. We'll say it's pointing north, right? But of course, it's actually magnetic south. But then all of a sudden, when you turn on the light switch, all of a sudden the compass needle doesn't point north or magnetic south anymore. Rather, the compass needle starts pointing in a direction like this. And you're like, well, what just happened? So you're fiddling around. You can't figure out what just happened. You turn off the light, and you look at the compass, and the compass is pointing this way again, towards the north or towards magnetic south. You flip on the light again, and the compass needle starts pointing this way again. And then you figure it must have something to do with this wire. So we move the wire. We reverse the wire. We put the lamp up here this time, and the wire's coming down through the same path. We turn it on, and all of a sudden now, the compass needle is pointing this way. We put the wire through right here, and maybe now the compass needle is pointing this way. Clearly the wire must have something to do with it, but it's not just the wire, it must be the electrons that are flowing through the wire, the electric current. It only worked when I had this wire, when I had this lamp turned on, right? So it must be the electric current flowing through it. The only logical conclusion really to draw from this is, since the compasses work on principles of magnetic field, they point in the direction of the magnetic field, is that this electric current, when it's turned on, generates a magnetic field. Well, that was the discovery that was made 200 years ago this year by Hans Christian Oersted. His discovery was, by accident, that magnetic fields are generated by electric currents. You have moving charges, which are electric currents. We will produce magnetic fields. He went on to do some more experiments with this. It wasn't just good enough to him to know that there was a magnetic field generated. He wanted to know what the direction of this magnetic field would be, what the shape of this magnetic field. It was well established what the shape of the magnetic field was surrounding a bar magnet. What does the magnetic field look like surrounding a wire? Well, the shape of the magnetic field is circular. It's a series of concentric circles. We'll draw that in just a moment. The direction, we'll figure that out in a moment as well. But the shape would look like this. What's that X mean? We talked about that after a quiz last unit. What does that X mean? Yeah, it means it's going into the page. Remember the dart? The dart is going away from you. It appears to be kind of like an X. It's going into the page. So the magnetic field shape is circular. Here's one magnetic field line. Here's another magnetic field line. Here's another magnetic field line. Notice they get progressively further apart. Well, the density of the field line simply indicates the strength, and that should make sense to us that the further you get away from the wire or the electric current that's generated in the magnetic field, the weaker the field's going to be. The shape of the magnetic field is circle. It's concentric circles, meaning that you have one field line that's a circle, then you have another field line that goes around that circle, and then you have another field line that goes around that circle, and so on and so on and so on. As you get further and further away, they get pretty far apart, indicating that the field gets pretty weak as you get further and further away. Well, how do we find the direction now? It was easy when we have just a bar magnet, right? The direction is the direction that a compass needle points are away from the north and toward the south. Well, I don't even see a north and a south here. So which way does this point? Oersted derived a law that we call, or a rule, I should say, that we call the wire grasp rule, which helps us to determine the direction of the magnetic field. He experimentally determined that if I do certain things with my hand will always predict the direction of the magnetic field. Here's how the wire grasp rule works. We take our thumb I want everybody to do this right now. Put your thumb in the direction of the moving charge. So in this case, we see the moving charge is into the board, right? It's represented by an X. The current is into the board. We'll say the direction of the moving charge or the direction of the electric current. Now keep your fingers at 90 degrees to your thumb. We're going to learn 3 rules this unit involving the hand. Okay, all 3 rules, my fingers have to be 90 degrees to my thumb. Now that doesn't mean my fingers can't do something like this, but you can still see the angle between my fingers and my thumb is going to be 90 degrees. Got it? So put your thumb in the direction of the moving charge, which is into the board in this particular case. The way that you have it drawn on your page, it would be like this, right? Into the page. Doesn't really matter. We're going to get the same answer whether we're looking at the board or whether we're looking at the page. Now what I want you to do is bend your fingers. So thumb in the direction of the particle, bend your fingers. Doesn't matter how much you bend them. Okay, some people I see haven't bent like this. Some people haven't bent like this. Doesn't matter. Just bend your fingers. Your bent fingers will point in the direction of the magnetic field that is caused by the moving charge. Now, how can we say that it doesn't matter how much you bend your fingers if your fingers are going to point in the direction of the magnetic field that's caused by that moving charge? If somebody bends their fingers this much, oh, the magnetic field is pointing this way. Somebody bends them more, the magnetic field is pointing this way. Okay, how can they both be right? Well, let's see here. Stick your thumb in the direction of current here. Fingers point in the direction of the magnetic field. Right now, my fingers, the way that I have them bent right now, are above the wire, and they're pointing to the left. If I bend them a little bit more, then they're beside the wire and pointing down. If I bend them even more, then they're below the wire and pointing to the right. See what's happening here? Doesn't matter how much you bend your fingers, the magnetic field in this particular case is going to be counterclockwise. Okay, I saw you bend your fingers quite a bit, right? I saw a few other people bend their fingers just a little bit. In the end, your fingers are pointing counterclockwise no matter how much you bent your fingers. Does that make sense? Just make sure they're not straight. Okay, make sure they're perpendicular to your thumb, and make sure they're bent. A little, a lot, whatever makes you feel good. Yep. That's a good question. If it's a negative particle, use your left hand. So an electron, use your left hand. When we're talking about an electric current, we're typically talking about negative particles, so it would be our left hand. But we could be trying to find the direction of the magnetic field caused by a proton or a helium ion moving through the air or a sodium ion moving through the air. They generate magnetic fields as well. Because those are positive, we'd use our right hand for that. So our left hand is used whenever we have negative particles. Our right hand is used whenever we have positive particles. We do the same thing with it. We just do it with the opposite hand. Now, how do you remember that? Well, there's no good way to remember that. Somebody a couple of years ago said to me, saying, well, here's how I remember it. They said, when I think of, especially in physics 20, but even in physics 30 when we were doing forces and we were doing momentum, when I think of left, the direction left, I assign a negative sign to that, right? Well, it's not the same thing here. Not at all the same thing, but it might be a way to remember it. Yeah, I use my left hand when I have a negative particle, just like a direction to the left is assigned a negative value. Left goes with negative, right goes with positive. Do a couple of examples on our paper here. We see a negative part. All these, let's say, are negative particles. Positive particles, just use your right hand. Okay, no different, except to use your right hand. We got a negative particle in the first example here. What does that X represent? It's going into the page, right? The magnetic field surrounding that is circular. I'm only drawing one field line there, but you know that there's multiple field lines, right? There's a series of concentric circles around that. I'll draw one because they're all pointing in the same direction. Now, which direction is that? If it's a negative particle, you can use our left hand wire grasp rule, stick our left thumb in the direction of the particle, which is into the page. Bend your fingers. How much? Doesn't matter. Right now, I bend my fingers a little bit, they're pointing up. Right now I bend them more, they're pointing to the left, and so on. Which way are my fingers pointing no matter how much I bend them? Counterclockwise. It's going to be this way. You can either label that, or you can just use the word counterclockwise, or the abbreviation for counterclockwise. Now, what does this middle one represent? This one's going not into the page, it's coming out of the page, right? It's that dart coming towards you now, right? You visualize that dart through in slow motion coming towards you. It's represented by a dot. It's a circular magnetic field that surrounds it again. What's the direction of the magnetic field? Thumb out of the page, fingers go, it doesn't matter how much I bend them, my fingertips are going to go clockwise this time, right? You good? Make sense? And then this one, well, we got our negative particle going to the left. I want to find the direction of the magnetic field above the wire, below the wire, in front of the wire, and behind the wire. So let's take our wire, look like this. Where are my fingertips right now? Behind the wire. Which way are they pointing? Up. I'm going to draw that as a broken arrow. Do you see why it's a broken arrow? A broken arrow means that we can't really see that one small section of the arrow because it's behind this wire that's pointing to the left. So behind it, it's pointing up. Now, where are my fingertips right now? Taylor, where are my fingertips this time? Yeah, where are they though? In front of the wire, and they're pointing down. I'm going to draw that as a solid line, okay, because that's in front of the wire. I can see the entire line this time because it's in front of the wire. Now, where are my fingertips right now? Where are my fingertips? Where are my fingertips right now? Underneath, below the wire. Which way are they pointing? Out of the page. So we're going to go below the page, below the wire, out of the page. Is going to be represented by a dot. And right now my fingertips are above and they're pointing into the page. So right above it, we're going to indicate it by an X. Some of you are probably pretty good at drawing this as a circle. Some of you maybe not so much so. You might want to draw it something like this. See what I've done there? In the end, as long as you express which way the magnetic field is going, it doesn't really matter whether you use the notation that I used right here or whether you're good at drawing the circle like that. It doesn't use words. You might just say, in front of the wire, it points down in words. Okay, as long as you can express that correctly in some way, it doesn't really matter how you do it. Yep.
Would it on top of the wire, or can you kind of towards you?
Yes. Yeah. So it's kind of drawn. That's the tough thing with drawing it like this, right? I'm trying to draw this as a three-dimensional diagram there. So it's up in the back, down in the front, which means it's coming out of the page in the top, right? It just doesn't look like that in this picture because I'm not a very good artist.
For the X, though, in the dot, right?
Yeah. Oh, yeah, that's reversed, I think, isn't it? Do I have those backwards? Yes, I do. Thank you. Yeah, this should be out of the page, and this should be into the page at the bottom, right? Let me just double check that again. Fingers below the wire are pointing into the page, yes, and above the wire they're pointing out of the page. Yeah, thank you. It's just a test. I can't believe one person passed that test. Okay, that mistake that I made on purpose. See who could figure it out. We good there? Okay, let me do one more, and then I'm going to set you to work on just a couple examples on a worksheet here. Let's say we have a positive particle moving up the page. It's not through a wire, but we'll just kind of draw it that way because it's easier to visualize. It's a positive particle going this way. We want to find the direction of the magnetic field surrounding this wire. Let's use our right hand. Okay, right now, where are my fingers? My fingertips, not my finger. My fingers are kind of bent, right? So where are my fingertips? Yeah, they're into the page, but where are they? To the right. To the right, they're pointing into the page. All right, let's turn them around this way. Where are my fingertips this time? Where are they? To the left. Where are they? To the left of the wire, and they're pointing which way? Out of the page. Good. So that's going to be a dot. Where are my fingertips right now? Sometimes it's easier to actually take a ruler or a pen or something to have a little manipulative. You remember back in junior high, you used to use these manipulatives in math class and so on? Sometimes it's easier to do that. We take a physical ruler here, we put our fingers behind the ruler, behind the wire, and they're pointing to the left. And then we bring them out front, and they're pointing to the right. Let's have a look here. Number one says, draw the magnetic field surrounding the wire showing the electron current below. Electron current is the flow of electrons. By the way, there's another term that I should have mentioned called conventional current. Electron current is the flow of negative particles. Conventional current is the flow of positive. All right? Make sense? So if you see electron current, use your left hand. If you see conventional current, use your right hand. This is electron current. We're going to use our left hand for this. We're going to find the direction. We're going to find the direction of the electron current. First of all, we know that it's a circle going around it. It's a bunch of circles. We'll draw it as one. Thumb in the direction of the particle, which is into the page. Fingers that are bent are going to point which way? Yeah, it's going to point this way, which is counterclockwise. I don't care if you use the term counterclockwise or you just label it on your picture, whatever, as long as you know what direction it's supposed to be. Electron current in this one as well. This is circular as well. This time we got our thumb pointing out of the page, because remember, you're visualizing that dart coming towards you now. It's a dot, so representing the dart coming towards you. Okay, thumb out of the page. Fingers are going to be bent a little bit, a lot, doesn't matter. They're going to go this way, which is clockwise. So inwards, by picture, whatever, doesn't matter. 3, find the direction of the magnetic field surrounding electron current below. Indicate the direction of the field above the wire, below the wire, in front of the wire, behind the wire. So left hand. Okay, right now, where are my fingers? Where are they? They're above the wire. Which way are they pointing? So let's put an X. Let's put an X there above the wire. They're pointing into the page. Right now, where are my fingers right now? Below the wire. Which way are they pointing? Out of the page. So we're going to put a dot right there. Right now, where are my fingers? Whoops. My thumb was going the wrong way though, right? Where are my fingers right now? In front of the wire. Which way are they pointing? Up, yeah, toward the top of the page. So I'm going to draw an arrow upwards like this. Now, this is where it gets interesting. Okay, you're doing this, and it's like up, and it's like, then you try to twist your hand down like this. You tear a muscle somewhere in your arm. Might just be easier to turn your body a little bit. Okay, where are my fingers right now? Behind the wire, and they're pointing down toward the bottom of the page. So that's what it would look like. Graphically, that's what it would look like. If any of you used words to describe it, that's okay as well. If you drew the little circle around it and you're good at drawing the circle around it, that's okay as well. 4, find the direction of the magnetic field surrounding the moving alpha particle. Hey, what's the difference here? An alpha particle is a positive particle, which means, Andrew, we got to do what? Yeah, it means we got to use our right hand. So we're going to switch it up here. We're going to say right thumb toward the top of the page. Fingers right now are to the left of the wire, and they're pointing out of the page. Right now my fingers are in front of the wire, and they're pointing towards the right. Right now my fingers are to the right of the wire, and they're pointing into the page, yeah. And right now my fingers are, here we go. Turn it around here. Right now my fingers are behind the wire, and they're pointing towards the left. So it's going to look like something like this. Good? 5, the diagram below shows the magnetic field surrounding a moving electron. So that's a negative particle. We're going to use the left-hand wire grasp rule. Okay, left hand. Oh, but wait a second. We want to find the direction of the electron this time. How do we know which way to stick our thumb? We don't. It's kind of like algebra. It's kind of like taking the equation v equals d over t and rearranging it to solve for d. Here we've got thumb fingers. Usually we stick our thumb in a certain direction, see which way our fingers point. This time we're pointing our fingers in a certain direction, see which way our thumb points. So this time we're going to go thumb, fingers 90 degrees to each other, bend my fingers, and then make sure my fingers are going clockwise. My thumb must automatically point out of the page in order to accomplish that, right? So we would say the magnetic field is clockwise. The direction of the electron current is pointing out of the page. Does that make sense? Good? And 6 shows the magnetic field surrounding an alpha particle. Alpha particle is a positive particle. So we're going to use our right hand for this. Stick our thumb, fingers, 90 degrees to each other, bend your fingers a little bit. Let's make sure my fingers are pointing clockwise. My fingers are pointing clockwise. My thumb must automatically point which way? Must automatically point into the page. Make sense? This might not seem like a big deal what we've just done. This discovery that was made 200 years ago this year by Hans Christian Oersted. But it is. This is, I would argue, perhaps the single most important technological, not scientific necessarily, but technological discovery in the history of the world. The reason I say that, it's definitely up there in the top 3 or 4, okay, maybe even the top 1. Okay, why is it such a big deal? Because just about everything that we rely upon today, just about every piece of technology that we have today relies at least in part on this discovery. Okay, we don't have our cell phones if we don't have this discovery. We don't have our computers if we don't have this discovery. We don't have anything electronic. We don't even have a bloody doorbell, like somebody to ring our door if we don't have this discovery. Just about every bit of technology that we use today relies at least in part on the fact that electricity generates magnetism, and the fact that we can predict what the magnetic field looks like, what direction it points as a result of that.